Alright, in this video I'm just going to quickly look at serial in, parallel out, and parallel to serial. So serial in, parallel out, SIPO first of all. If we look at a 4-bit version, then we're going to have 4 flip-flops. So what happens is the data comes in, so serial in comes into the first flip-flop, and then it's going to come out of that flip-flop. Oh, there we go. And we need to delete the arrow. So it's going to come out there into the next flip-flop. Okay, and so on and so forth. Into D and to Q and to D, like so. And how is this going to manifest itself with the different things? Well, the first flip-flop here is going to be my A flip-flop, my B flip-flop, my B flip-flop, and my C flip-flop, and then the D. So that's being the most significant bit. This is being the least significant bit. Okay, so in terms of what goes in, in terms of this, the most significant bit is going in first into it. Okay. How do we then clock it? Well, all of the flip-flops are synchronously clocked, so all the clocks are connected together like so, and that is our SIPO like so. So in terms of signals, let's have a look at what we've got. So I'll just pause the video so we can. So if we look at it in terms of a table to start with, then if this is our word DCBA that we want to load in, 1101. So the most significant bit is going to be going first. So on the 0 clock pulse, we're going to have a 1 waiting on the serial in. After the first clock pulse, then that is then going to be clocked in, and it will be at output QA, and there'll be also then another 1 waiting at the serial input. If we then clock that again, then that 1 then that we had, the 1 that we've got here, then gets transferred to flip-flop B. The 1 that was waiting on the serial in gets then transferred to QA, and then the next value on the serial in is our 0. Okay, we clock the flip-flops again, so that 0 that's at the serial in gets transferred across to there, and the 1 and the 1, and what's waiting to come in is this final 1 that we've got there. And then we clock the flip-flop again. Well, we've got nothing else coming in, so then that can be transferred across like so. So we end up with seeing what we've got, the value that we've got here, backwards on to how we would normally see it, because the most significant bit is on flip-flop, the final flip-flop. Okay, so we'll see that in a timing diagram as well as a table. So you can see that I've just drawn a quick timing diagram there. So I've got my clock impulses, I've got my serial signal that I've got, so that then as soon as I clock my flip-flop, then QA will go to a 1, okay, and it will then obviously clock through, and we're going to keep that 1 there. We're going to clock it through, we're going to keep that 1 there on flip-flop 1, and then at this point here in time, we'll flip-flop A, it goes to a 0, and then we clock it, and it's going to go back to a 1. And if we trigger our flip-flop again, it would go to a 0. So notice I've just done the whole of QA all in one go. So then QB we're going to have the same thing. So nothing's going to happen until this 1 then traverses through onto flip-flop B. So it'll be on the second pulse there that flip-flop B then sees sees this 1 coming through. And then it stays a 1, stays a 1, stays a 1, and then it's not until this 4th clock pulse that that QB will then go to a low, so we get a signal like that. Don't know what's going on with the mouse. And then finally QC, the signal eventually gets clocked through just here, and QD finally gets clocked through there, like so. And that's what it looks like as on a timing diagram. Okay, right. Let's look at a parallel to serial. Okay, so here is the parallel in serial out. It's a 4-bit. I've partially completed it. So initially, the first data input is going to have 0 volts on it, so that we can do our stop bits. We've got serial out, so we're connecting our Q's to D's on all of them. But then we've got this load line here, and sometimes called parallel load, PL. And then we've got our data input, so D0, D1, D2, D2, and D3. Okay. So what happens here is that we put the data that we want to load into our parallel in serial out, so that it's all there on the D0 to D1, D0, D1, D2, D3. When we've got the data on there, then we enable the parallel load by making it high. So what we've got on our D inputs then is allowed through the AND gate to the set input on our flip-flops. So that's going to set the relevant flip-flops or not set them, as as it may be. If there's obviously the data input is a 0, and then once we've done that, we can then take the parallel load, make it at low, and then we can then clock through the bits that we've got. Okay, so we'll just show you that in a form of a diagram. So we load the information in to start with here. Load the information in. Once we've loaded the information, we take the load low, and then we can clock the data that we've got, that we've loaded in, through each individual flip-flop, like so. So it's okay. So for this example, I'm going to be using 0110 as my word that I want to go out. Now, obviously, important thing to look at on our parallel and serial out, that the most significant bit goes out first. Okay. So the first thing that's going to happen is I'm going to my load signal parallel load. I'm going to make it go high, so that therefore then I load into my flip-flops that information. Okay, because set has priority over everything else, and then I can then clock the information through. We clock the information through. So on the first clock pulse, then that 0 that's on D is going to go out, and then the next bit is, so we're going to have a 1 from the flip-flop C, then transferred to flip-flop D, so that's going to go out, and the 1, so everything shuffles down. The 0 there that was on flip-flop A is now in flip-flop B. Now, because flip-flop A is connected to 0 volts, the D input, then every time we clock our clock, then we get a 0 volts, and we get a 0 there on it. So then on the second clock pulse, everything shifts down again, so the that's gone now, that's that there. So flip-flop C is now out, and we've got the 0s, 0, 0, and then we loaded another 0 volts in. So on the third clock pulse, we're now going to output the final 0 of our word, and then after the 4th clock pulse, then we can output the 0 to say that everything has finished. Okay, so we can see that then finally in a timing diagram. So I've just drawn what my initial states of QA, QB, and QC are, QD are after we've done the load. So once we do the load, then on the first clock pulse, then the value, the 0 that's on QA will then get clocked through to flip-flop B. So then flip-flop B will go low like so. The high that was on flip-flop B will gets clocked through to flip-flop to again, so we can go all the way to this point here. And then on that second clock pulse, the low that's on flip-flop B, and because obviously flip-flop B is going to stay low, and obviously we can remind you why the flip-flop B output will stay low, is that then gets flipped onto flip-flop C, so that's going to go low at that point there and then stay low like so. And flip-flop D, the high there that was on flip-flop C will get clocked through at that point there, so that's going to get clocked through, and then that's going to then stay there like so, and it's then not going to be until the 3rd clock cycle that this then goes low like so. And of course QA is going to remain low because every time we have a clock cycle we get a 0 go through. So as a timing diagram it will look a little bit like that. Fabulous. Unfortunately these videos end up being a little bit longer, but hopefully breaking it down works the job.